All right, welcome back. Today we're jumping headfirst into a really cool linear algebra problem that honestly feels more like a detective story.
So, what's hiding inside this matrix equation? Well, you can think of it like this. This equation, ax plus xa equals c, it's basically the set of rules for a very exclusive club. And our job? We're the detectives hired to figure out the secrets of this club.
Okay, first things first, let's get the lay of the land and meet the key players in this mystery.
So at the center of all this is a set we're calling U. And like I said, it's basically this exclusive club for square matrices. For a matrix, let's call it X, to get in, it has to pass one simple test. AX plus XA has to equal C. That's the password, the secret handshake, the whole deal.
All right, let's open our first case file. We've got a person, a matrix of interest, named B. And here's the kicker. B is already inside the club.
So, the file on B gives us a couple of critical clues. We know B is a member, so AB plus BA equals C. Check. And here's the big one. B and C are partners in crime, you could say. They commute, meaning BC equals CB. So, what's our mission? We need to prove that this relationship implies another secret connection, that A and B squared also have to commute.
But hold on, before we go any further, what does it even mean for matrices to commute? It's actually super simple. It just means the order you multiply them in doesn't matter. So P times Q is the exact same as Q times P. Easy, right? But believe me, it's a really powerful idea.
So how do we connect the dots? Let's walk through the proof together. We start with our target, AB squared. Now, we know B is in the club, so we can rearrange the club rule to say AB equals C minus BA. Let's plug that in. That gets us to C minus BAB, which is CB minus BAB. See that other AB in there? Let's substitute it again. So now we have CB minus B of C minus BA. Expanding that out gives us CB minus BC plus B squared A. And now for the final move. Remember our key clue? CB equals BC? So those first two terms, they just poof, they cancel out. And what are we left with? Just B squared A.
And there it is. AB squared equals B squared A. They commute. Case closed on part 1 of our mystery. Pretty neat, right?
All right, but the story doesn't end there. The plot is about to thicken because we just got some new intel.
Okay, so here's the new info. First, matrix A is invertible, meaning it has an inverse. That's a huge piece of information. Second, it turns out B squared isn't just a side character, it's also a full-fledged member of the club U. This opens up a totally new line of inquiry, a really surprising one. We have to prove that the trace of B squared is the same as the trace of B, and trust me, the trace is a big deal in math and physics.
To crack this part of the case, we're going to need a special tool from our detective kit, the idea of similar matrices. Now what are they? Think of them like identical twins who might wear different clothes. They might look a little different on the surface, but they share the same fundamental DNA. And for us, the most important piece of that DNA is that they always have the exact same trace. That's the key right there.
Okay, so let's put this new tool to work. First, we pull together everything we know. We know B is in the club, so AB plus BA equals C. We also know B squared is in the club. And since we already proved AB squared equals B squared A, that second rule simplifies down to just 2AB squared equals C. So look at that, we have two different things that both equal C. Let's set them equal to each other. AB plus BA equals 2AB squared. Now just a little bit of algebra. Let's shuffle things around to get BA by itself. That gives us BA equals A 2B squared minus B. And for the grand finale, remember that new intel? A is invertible. So we can multiply both sides on the left by A inverse. And what does that give us? A inverse BA equals 2B squared minus B.
And that right there, that's the smoking gun. Look at that equation. It perfectly matches the definition of similar matrices. We've just shown that B and this other weird matrix, 2B squared minus B, are officially similar. And since they're similar, you know what that means? They have to have the same trace. So TR of B has to equal trace of 2B squared minus B. Now, the trace has some nice properties, so we can split that right side up into 2 trace of B squared minus trace of B. Let's just move that trace of B over to the other side, and we get 2 trace of B equals 2 trace of B squared. Divide by 2, and bam, trace of B equals trace of B squared. Mission accomplished. Another case solved.
Okay, so we've been deep in the weeds, looking at individual members of this club. But now, let's zoom out. It's time to ask a much bigger question about the entire club.
You see, for this club U to be what mathematicians call a subspace, a stable, well-behaved structure, there are certain non-negotiable rules it has to follow. So the question is, what does that imply about our matrix C?
Well, there's one golden rule for any subspace, no matter what. It absolutely must contain the zero element. In our world of matrices, that's the zero matrix, literally just a matrix full of zeros. It's kind of like the home base or the origin point. So, if our club U is going to be a proper subspace, that means the zero matrix has to be a member. And to be a member, it has to pass the entry test, right? It's got to satisfy the rule AX plus XA equals C. So, what happens when we plug in the zero matrix for X?
Well, A times 0 is 0. 0 times A is 0, so the whole left side just becomes 0. And the equation becomes 0 equals C. And that's it. That's the big reveal of the whole mystery. For our club U to have this stable mathematical structure, C can't be some random matrix. It has to be the zero matrix. It's the only possibility. So let's take a final step back and just appreciate the beautiful logic we've just walked through.
I mean, think about it. We started with this one simple-looking rule for a club, AX plus XA equals C. And then, by following just a couple of clues, one about commutativity, another about invertibility, we uncovered all these deep, hidden connections. We found relationships between matrices and their squares, and between their traces, and in the end, we discovered that for the club to even exist as a stable structure, that C matrix was forced to be zero. It all just shows how these fundamental rules in algebra create these incredibly deep and predictable patterns. And that's really the heart of this explainer. It leaves you with a final, bigger thought, right? This idea that a few simple, fundamental rules can give rise to incredibly rich and complex structures. That's not just a math thing. You see it everywhere, from the laws of physics that govern galaxies to the simple code of DNA that creates all life. So where else do you see it? It's something to think about. Thanks so much for watching.